This is a video for probability day 7, practice with probability. Nothing in particular that's new in this lesson, but just taking a look at some different kinds of problems gives a chance to practice what we've been learning about probability and look at a few things that maybe we haven't seen before. We are going to start with this warm-up question. We haven't done a question exactly like this, so it's a good one to do. It says the table below shows the results of a survey in which workers between the ages of 26 and 45 were asked if they had at least 1 month's income set aside for emergencies. And we have this little chart here that shows the men versus the women, less than 1 month's income or 1 month's income or more. And then it says if two different workers are randomly selected, find the probability that they both have 1 month's income or more set aside for emergencies. Round your answer to the nearest percent. So you should pause the video for a moment and see if you can come up with an answer to this question. So go ahead and pause the video and give it a try. Okay, so I'm going to go down here and recopy this table, and then we can work this out here. Okay, so we've got less than 1 month, we've got more than 1 month, we've got men, we've got women. Okay, 66, 83, 76, and 62. Okay, so we want to find the probability that both of these workers, when they pick two different workers, have 1 month's income or more set aside. We want to figure out, right, the probability that someone picked at random has more than 1 month's income, right, and then when we pick another one, they also have more than 1 month's income set aside. So probability of more and more, right? More and more. Okay, so we need to figure out that if you pick a worker at random, one worker at random, they have more than 1 month's income set aside. So we need to get the total amount of people that have more than 1 month's income set aside. So if we add the 76 men plus the 100 or plus the 62 women, right, we get 138. So 138 workers have more than 1 month's income set aside. Okay, we then have to divide that by the total. So to get the total, I have to add the 66 plus the 83 plus the 76 plus the 62. So if you add up all of those, you're going to get 287. Okay, so the probability that one worker picked at random has more than 1 month's income set aside is 138 out of 287. Okay, then we're going to pick another worker, right? Except that we're picking two different workers, which means that we're picking without replacement. And then this is an and situation, right? So we should be multiplying. Right? So when I pick the second one, assuming that the first person I picked had more than 1 month's income set aside, that means that now there's going to be 137 workers left that have more than 1 month's income set aside. And then the total would now be, oopsies, 286. Okay, subtract 1 from both of those basically. Okay, and then you're going to multiply both of those fractions together. If you put that into the calculator, you get 0.23033. Some other stuff there. It did say round your answer to the nearest percent. So we're going to take this decimal, multiply it by 100. So we'll get 23%. So your final answer there is going to be 23%. Okay, moving on to the notes. So we're going to start by reviewing all of the probability rules that we've been learning, because it can be a lot to keep track of. So we have given event A and event B. First, the probability that event A or event B occurs. Okay, so when you see an or probability, you have to think about adding as the operation involved. You know, this was what it looks like in words. Symbolically, this would be probability A union B. If we think about what we're talking about on a Venn diagram, right, if we have A and B, A union B is everything all together. So it's anything that's in either one of these circles, including the middle portion. Right? So union is everything. Okay, now they've broken it down into mutually exclusive and not mutually exclusive. The answer actually ends up coming out to be the same either way, but it's good to talk about the difference there. And to remind you what mutually exclusive means. Okay, mutually exclusive means that our sets have no overlap. There's no intersection there. Right? So set A and set B totally separate. So that means when you go to compute your probability of A or B, you're just going to take the probability of A and you're going to add it to the probability of B. If they're not mutually exclusive, right, then it would look something like that. So the most important thing to remember is that, and really if you can just remember this, it'll work for both, right, that the probability of A union B, right, means I have to take the probability of A, add it to the probability of B, and then I have to subtract this overlapping section because now that just got added on twice, right? So I'm going to subtract probability of A intersection B, probability of A and B. Okay, so if you can remember this, you know, it really works for both. It's just that when you have mutually exclusive, this overlapping part is 0, so it ends up going away. Okay, but it's really the same rule for both. But you do have to know what mutually exclusive means and know that there's no overlap there. Okay, so OR means add, and then we have to remember to subtract the overlap if there's any overlap. Okay, if we want to compute an AND probability, like we just saw in the warm-up, right? AND means we're thinking about multiplying. Right, we got to multiply our probabilities together. Symbolically, probability of A and B with the intersection symbol. Okay, we've got independent versus dependent. And they're really the same thing, but it's two different formulas depending on whether you have independent or dependent events. So, multiplication rule, right? Probability of A and B is equal to the probability of A times the probability of B. So if your events are independent, you can just multiply them together, the two probabilities. If they're not independent, we're still multiplying. And so it really is the same thing. It's just that I would take probability of A and then probability of B is going to be affected by the probability of A. So I have to work my conditional probability in. So if they're not independent, the probability of A and B happening together is the probability of A times the probability of B given A. And so there's a little alternating happen with the letters, if that helps you remember. Yeah, it's really the same idea. It's just that if there's a dependent probability involved, if they're not independent, then you got to work that into the formula, that's all. So OR means to add, AND means to multiply. Okay, then we learned our conditional probability formulas. So what's the probability that A occurs given that B occurs? Probability of A given B. Okay, so that's the probability of A and B, so the intersection, divided by probability of B, the second one. So probability of the intersection divided by the probability of the second one there. Okay, same thing for probability of B given A, we're just going to switch our letters around. Right, so this would be probability of B and A divided by probability of A. Okay, yeah, you just remember that, you know, one formula, just adjust it based on the letters that you're working with. Okay. And then lastly, we have our test for independence. Again, independent events means that A and B have no effect on each other. Completely separate events that do not affect each other at all. They have no effect on each other. So the easiest way to test for independence is to check this conditional probability. Because if A and B are independent events, right, when you try to figure out the probability of A given B, right, you're just going to end up with probability of A again, because B had no effect on it whatsoever. So if probability of A given B is equal to probability of A, then A and B are independent. Or you could go the other way as well, depending on which information you have. Probability of B given A would be equal to the probability of B. Again, either one of those depending on which information that you have. As we mentioned yesterday, you could also use the product test. You could also use product test every once in a while, and they ask about that. So you could refer to your multiplication rule and use this as a test for independent. Check to see if your probability of A and B together is equal to the product. Again, the issue with this is it doesn't work 100% of the time, which is why I prefer to do it this way overall, but every once in a while they do ask about that. Okay, so now we're going to look at some problems. Again, mostly along the same lines of what we've been doing, a few little twists to give us a chance to practice some of this stuff. So a survey of registered voters in a city in New York was carried out to assess support for a new school tax. 51% of the respondents supported the school tax. Of those with school-aged children, 56% supported the school tax. Now, only 45% of those who did not have school-aged children supported the school tax. And then we have some questions to answer. So I want to try to write down sort of what information they're giving me. I'm going to let S represent probability that someone supported the school tax. Okay, so probability that someone supports the school tax is going to be 0.51. Then it says, of those with school-aged children, so I'm going to let C represent anybody that has children. Okay, so of those with school-aged children, 56% supported the school tax. So that means the probability that a person supported the school tax, given they had school-aged children, was equal to 0.56. And then finally, oops, at least I have enough room here. Okay, 45% of those who did not have school-aged children supported the school tax. I'll have to put that over here. So probability that they supported the school tax, given that they did not have children, C complement, that's what's equal to 0.45. Okay, so now we'll see if we can answer these questions. So if a person who responded to the survey is selected at random, what is the probability that the person selected supports the school tax? So the probability that someone picked at random supports the school tax, that's P of S. So P of S, 51% or 0.51. So that's all they're looking for there. What's the probability that the person supports the school tax given that he or she does not have school-aged children? Well, they told us that as well, right? Probability of they support the school tax given that they do not have children is 0.45. Okay, part B says, are the two events has school-aged children and supports the school tax independent? So think for a second. We just reviewed it. How do we test to see if two events are independent? If I want to check for independence, I'm going to check my conditional probability. So again, I have, oopsies, school-aged children, which is C, supports the school tax, which is S. Now I can do it in any order, right? But if I look up top at the information that I happen to have this conditional probability sitting right here. So I'm going to use this one. So probability that they support the school tax given that they have school-aged children, I'm going to check to see, is that equivalent to the probability that, again, if you're picked at random, you support the school tax. Okay, so from above, probability of S given C is 0.56. Probability that they support the school tax is 0.51. Okay, those are not the same. So therefore, those events are not independent. So the probability that you have school-aged children affects whether you support the school tax or not. That's what we just showed. Okay, and then suppose that 35% of those responding to the survey were over the age of 65, and 10% of those responding to the survey were both over the age of 65 and supported the school tax. What is the probability that a randomly selected person who responded to the survey supported the school tax given he or she was over age 65? Okay, so more information to sort out here. So probability that they were over the age of 65 is 35%. So this is just a probability that someone picked at random that answered the survey was over 65 is 0.35. And then the probability that a person was over the age of 65 and they supported the school tax is 10%, so 0.10. And then we want to know what's the probability that a randomly selected person who responded to the survey supported the school tax given that he or she was over the age of 65. So probability that they support the school tax given that they were over age 65. Okay, so to figure this out, I'm going to use my conditional probability formula. So that's probability of school tax and over 65 divided by the probability that they were over 65. Okay, and I have both of those pieces of information right here. All right, so 0.10 divided by 0.35. If you put that into your calculator and math bracket back, you're going to get 2 over 7. Right, it's approximately 0.29 as a decimal. It didn't say anything about rounding, so easiest to math bracket back into a fraction. Do that. Okay, on to the next question. In contract negotiations between a local government agency and its workers, it's estimated that there is a 50% chance that an agreement will be reached on the salaries of the workers. It's estimated that there's a 70% chance that there will be an agreement on insurance benefits. There is a 20% chance that no agreement will be reached on either issue. Okay, so yeah, I'm going to convert this into some symbols so I can keep track of what's going on. How about S for salaries, I for insurance? Okay, so probability that they reach an agreement on the salaries is 50% or 0.5. Probability that they reach an agreement on the insurance, 70% or 0.7. And then there's a 20% chance that no agreement will be reached on either issue. So not S and not I. So how about probability of S complement and I complement? So not S and not I. That's 20% or 0.2. Okay. And part A says to find the probability that an agreement will be reached on both issues. Okay, so I want to find probability of S and I. That's what I'm trying to compute. Okay, so this is the question. I have two options, right, for figuring out probability of S and I. But it depends on whether those events are independent or dependent. And unfortunately, I don't know that right now. They didn't give me any of that information, right? So I don't know dependent versus independent, so that's a problem. I could test that if I could figure out my conditional probabilities, right? But they don't tell me that, and unfortunately, I don't have enough information to figure that out either. Because if you think about what the conditional formula is, right, it involves this. So I'm out of luck. All right, don't know. Can't find the conditional probability. So I'm kind of out of luck with all the other stuff we've been doing. Can't use any of those formulas to help me answer this question. Okay. But, you know, they did give us one other piece of information here, which has to be helpful somehow. That this 20% chance that no agreement will be reached on either issue. Okay, so let's see if we can break that down and think about what that means. So, probability of not S and not I. If I were to draw that with a Venn diagram, way too small. Okay. So like here's S and here's I. Not in the S circle and not in the I circle. That's all of this that's around the outside. All right, that's what we're talking about. Can't be in either the S circle or the I circle. Does it make sense that that's the same thing then as saying that's the probability of S union I complement? right? Because the opposite of S or I, again, is this outside part. So this is just another way to represent this, right? If I said, show me S or I complement, you say, oh, it's got to be on the outside. It's the opposite of the two circles. Okay, so I know that's point 2. So how does that help me? Well, I know then that I can figure out what this probability is then when I put the two circles together, because the probability of something happening plus the probability of that thing not happening has to add up to be 1. So probability of S or I plus the probability of S or I complement has to add up to be 1. So I can then figure out, if I know that this is 0.2, right, 1 minus 0.2 is equal to 0.8. So that 0.8, that's what probability of S or I, S union I, is going to be equal to. So I'm using my complement probability trick there. So now I know another piece of information. Okay, now that I have this information, I can actually get to this. And there's a couple different ways you could do it. I'll show you 2 different options. One way to do it is to consider our addition rule. Oops, go away. Okay, so what I just figured out is that if I add up all these the circles, including the overlapping part, I get 0.8, right? I have some totals up here. That'll help me figure out what this overlapping part is. That's what I'm trying to find. So based on our addition rule, right, I could use the fact that, okay, probability of S or I is equal to the probability of S plus the probability of I minus probability of S and I, right? Subtract the overlap. So since I know this now is 0.8, right, and from earlier, I know that P of S is 0.5 and P of I is 0.7, right? I can figure out probability of S and I, which is what I'm trying to do. So if you add 0.5 plus 0.7, you're going to get 0.12. Subtract that over. So technically it's negative 0.4 is equal to the negative probability of S and I. Okay, so therefore positive 0.4. So that overlapping section there is 0.4. And so I use my addition rule to help me figure that out. Okay, another way that you could do that is you could set up a Venn diagram with some X's to actually help you figure that out. Let's see if I have enough room to do this here. So I could have set up a Venn diagram. Here's my circle S, here's my circle I. Right, and basically what I'm trying to figure out is this middle section X. Right, it's going to label that with an X. That's what I'm trying to find. How could I use what I know? Well, probability of S is equal to 0.5, so that means everything in this S circle has to add up to be 0.5. So whatever this X is, that means that this has to be 0.5 minus X. And then if the total of the I circle is 0.7, that means that this section is going to be 0.7 minus X. And then I know that probability of not S and not I, which as we've mentioned is this outside section, that's 0.2. And then we know from our earlier work with Venn diagrams that everything in the Venn diagram always has to add up to be 1. So if I take all these little pieces, so 0.5 minus X plus the X in the middle plus the 0.7 minus X from the I circle plus the 0.2, they'll have to add up to be 1. Okay, and now I have an equation that I can use to solve for X. So if I clean this up a little bit, negative X, positive X goes away, so I still have a negative X left. 0.5 plus 0.7 plus 0.2 is 1.4 equals 1. So I get negative X equals negative 0.4, and therefore X is equal to 0.4, which is what we got up here. Okay, so a couple different options we could use to figure that out. This is kind of just thinking outside the box and how we can use what we know about probability to figure out some different stuff. Okay, we got one more question we need to answer about this. Based on your answer to part A, determine whether the agreement on salaries and the agreement on insurance are independent events and justify your answer. Okay, so if we're going to test for independence, again, we want to check the conditional probability, which we didn't have up here, but now that I have this information, I have a couple ways actually that I can figure that out. Okay, so if I want to test for independence, I'm going to say, okay, probability of that they get an agreement on the salaries given that they get an agreement on the insurance, right? Is that equal to the probability of just the salaries? Okay, and you've got a couple ways now you can solve this. You can use your formula, all right? Probability of S and I over probability of S. Or you can look at the Venn diagram as well. If we go back to this picture that we just used, right, and fill in now that we know what X is, right, so this is 0.4 in the middle, did not draw this big enough at all. So this is 0.4, that means 0.5 minus 0.4 would be 0.1 in the S circle, and 0.7 minus 0.4 is 0.3 in the I circle. You'll notice either way you use it, we're going to get the same thing over here in the next one. P of S, by the way, is 0.5. Okay, from up top. So, probability of S and I is 0.4. Right, and then the probability of, oh, sorry, that was supposed to be probability of I down here. Oops. Apologies. Probability of S and I over probability of I. Okay, there we go. And then the probability they get an agreement on the insurance is 0.7. If you go look at the Venn diagram and want to figure out probability of S given I, just to remind you, you could do that. Right, if you have this picture set up, what's the probability of S given that you're in the I circle? So probability of S in the I circle is 0.4, right? And then divide that by the whole I circle is 0.7. So there's two different ways really you can get to this 0.4 over 0.7. Okay, we're still checking to see if that equals 0.5, and if you put that into your calculator, you'll see that this fraction equals 0.57, which does not equal 0.5. Okay, so these are not independent events. Not independent. Okay, last question here. The results of a poll of 200 students are shown in the table to the right. For this group of students, do these data suggest that gender and preferred music styles are independent of each other? Justify your answer. So we've got all these different types of music. We've got females versus males. We know we can test for independence by using our conditional probability test. They're not telling us, they just kind of want a general answer. So what that means is we can really pick anything. So we're just going to pick, a group or a gender and a style of music. We're just going to pick something and test it. And really, you can pick any combination that you want. So just because it's the first square, right, I'm going to test, all right, so does the probability of being a female, given that the student likes techno music, is that equivalent to the probability that a student picked at random is a female? Again, you could pick anything. Probability that they're a female given that they like rap. Probability that they're a male given that they like techno. Does that equal probability of male? Yeah, you test anything. So let's see what happens. So if I want to figure out the probability that they are a female, given that they like techno music, I got to figure out some totals here, right? So I need to know the total number of people that like techno, which is 90 if you add 54 plus 36. Okay, so probability that they are a female, given that they like techno music. So I'm just looking in the techno column. So 54 out of the 90 students that like techno, that's the probability that you're female given that you like techno. Yeah, you could do it the long way too, figure out the other totals, which we're going to have to do in a second to figure out this. Okay, so I want to figure out that a student selected at random, probability that that student is a female, right? I got to get the totals. So if you add up the rap column, right, 65, add up the country column, 45. If you add 90 plus 65 plus 45, you end up getting 200 for the total. You also get the same thing if you go across the top. If you add up all the females, you get 106. And if you add up all the males, you get 94, right? Which also adds to 200. So 200 all around for the totals. Oh, and we needed that 106 because we need the total females, right? So 106 females out of 200 students total. And we're going to check to see if these probabilities are the same. Okay, in your calculator, if you do 54 divided by 90, you get 0.6. If you do 106 divided by 200, just give it away there, you get 0.53. So they are not the same, so therefore they are not independent. And you can just stop there, right? I suppose technically, if you were going to show that they were independent, you would have to test every single possible combination. But since we already found one that's not independent, we can just stop there and be done with it. Okay, that is the end of our day 7 probability practice.